Hi everyone, I am Madan Thapa Chhetri. Today we will deal with some of the problems related to pipe flow system, head loss analysis, and cavitation in hydraulic systems. So before we jump into some of the numerical problems that we are going to solve today, our main learning objective for this recitation class is we will learn how to apply energy equation to analyze complex pipe system that has multiple branches and components, and we will also use the Darcy-Weisbach equation for calculating the head loss and by determining the friction factor through the Modi diagram, and we will also use the equivalent pipe method for analyzing the parallel pipe networks. We will also identify condition where cavitation may occur and evaluate cavitation risks. We will also determine appropriate pump placement for avoiding cavitation problems. So some of the key concepts that we need to understand before we jump directly into numerical problems is we need to know about this energy equation. I think up to now all of you know about this energy equation, and second one is Darcy-Weisbach equation that help us to calculate the frictional head loss. So this is the formula in terms of flow rate and diameter, which will be used in later numericals. So you also need to take care about dimension and units of each terms. And another one of the important things to know before we jump into problems is about parallel equivalent pipe for parallel system, where parallel pipes head loss are equal for each branches, whereas for flow rate, suppose from A to B it flows 100 and it has three branches, let four branches, then after four branches merge into another, then in this case q is equal to q1 plus q2 plus q3 plus q4. So that's all about equivalent pipe system. And another fundamental is cavitation. It occurs when local pressure drops below the vapor pressure of liquid. For water at 20 degrees Celsius, the vapor pressure head is approximately minus 7 meter absolute, or expressed as a gauge pressure. And one of the key insight here is cavitation is most likely uh, at the points that has highest elevation and that has also highest velocity and after significant head loss. So uh, why cavitation is dangerous in hydraulic system? What physical damage can it cause? Because bubble collapse creates shock waves that can erode pipe walls and pump impellers. This can impact the aging of pipes, so cavitation is dangerous in hydraulic system. Now let's jump into the uh, numerical problems that we are going to solve. So first questions asks us about determining the total head loss due to friction from section A to B, from A to B head loss. And second one is to determine discharge in each of branch 1 and 2. So now let us rewrite or let us draw numbers into the figures. So for pipe AB, the length is 1000 meter, whereas flow rate is 60 meter cubic meter per second. Whereas in while going through BC, 20 meter cube per second is added. And for branch 1, diameter of pipe is 2 meter and frictional factor is 0.018, and length of this branch 1 is 1000 meter. Whereas for branch 2, diameter is 3 meter, frictional factor is 0.02, and this length is 800 meter. And since 20 plus 860 is added into BC, whereas through C 10 is left out, and final flow rate to CF will be just 70, and length of CF is 900 meter. And okay, so we understand the equations and we also analyze the flow. Now, since the pipe are in parallel combination, that means branch 1 and branch 2, both branches experience the same head loss. So let us assume, like for equivalent pipe, properties for BC, B, let us suppose like for diameter B 3 meter and frictional factor B 0.02. Now we know the concept of equivalent, where Q is equal to Q1 plus Q2, and I already mentioned uh, about head loss, and simplifying this Q is equal to Q1 plus Q2, we got like dE to the power 5 divided by F, E frictional factor, length of equivalent pipe, and underscore under root under half square. So this is the we got like final equation, and while uh, solving we got like a length of equivalent pipe is 444 meter, and we will use this 444 meter for determining the head loss from A to F. So now let us go back here. H F AF is combination of HF head loss from AF, AB, plus head loss from BC plus head loss from CF. Why we needed to calculate the length of BC is because we need to assume this as equivalent pipe, because we need to compute the head loss for AF. So we computed that, and by this we have head loss from A to F is equal to HFAB plus HFBC plus HFCF. And I already mentioned about the HF head loss formula for um, in terms of Q and D. So which, while simplifying, we got this like 0.083 times FL Q squared divided by D to the power 4. And by simplifying this, we will have the answer of 73.8 meter. And we put this length of equivalent pipe here in the for like HFBC. So since we know like HBC or HAF is equal to 73.8, HBC is equal to 19.3, and we know head loss for equivalent pipe is equal to head loss for branch 1 and branch 2. They are all equal. Now let us solve for head loss for H1 and H2. So that will give us the flow rate. Since we have head loss for HBC, let us talk about branch 1 first. We have 19.3, and this is frictional factor. Not this is 0.018 is frictional factor. This is constant that we already obtained from above. We have length of branch 1 is 1000 meter, and we need to find Q1. So this is diameter. So we have Q1 is equal to 20.4 meter cube, meter cube per second, and similarly for branch 2 as well, we have like q2 is equal to 59.6. So for verification, what we can do is q is equal to q1 plus q2. Q is our 80, so q1 plus q2 should be equal to 80. That make us verify our problem, and we solve the question number 1. And there can be one question that can arise: why does branch 2 carry more flow even though both branches have the same head loss? The answer will be like branch 2 has larger diameter and shorter length, so it has lower resistance to flow. Now let us go to question number 4.2.9. This is slightly before then the order of your homework problems, but I would like to solve this first. This problem asks us to determine maximum distance from reservoir A to this pump P such that there will not be problem of cavitation. And there is also given a design discharge which is 4.5 meter cube per second, and this diameter of pipe is 80 centimeter, which is 0.8 meter. So now we need to, our main intention is to find length of this from reservoir A to pump S. So we can use energy equation for this. So we have energy equation written in this form, where this HA minus HP will be a 4 meter, and since velocity and pressure will be 0, so we will neglect that. But for pump, our this pressure head and this velocity head, they are unknown up to now. But what we know is for having no cavitation, pressure head should be less than 7 meter. So we can use that for we can use this in later. So we have this equation 1. Our main intention is to find here, solve for B. We don't know the HF as well, we need to compute that. But since we are given design flow rate, we can use Q is equal to AV. So velocity will be equal to 88.95 meter per second. And this HF or head loss will be equal to head loss from major plus head loss from minor. So this gives us this equation, Darcy equation, plus this K plus B squared by 2G is for minor head loss. So we know B, we know L, D, we know everything except F. F is unknown. So what we can do is we can use surface roughness, which is equal to E by D for rough concrete with round pipe of rough concrete. We can use E of 0.6 mm, and diameter of pipe is 800 millimeters, so that gives us 0.00075. Similarly, while calculating the Reynolds numbers like dV by kinetic viscosity, we know kinetic viscosity at 20 degrees Celsius, so which is 1 times 10 to the power minus 6, and we know diameter and we know velocity. So from this we get 7.16 times 10 to the power 6. This confirms that the flow is turbulent, and by using this surface roughness and Reynolds number, we can compute frictional factor F from Moody chart, which will be equal to 0.0185. And we also know this Ke, which is 0.5, for square is 5. So this HL will be equal to, just putting all the value that we have got except this L. L is the value that we need to find. So here I think I missed 0.094. Here it should be L. Here it should be L. Okay. And we have this HL equal to 0.094L plus 2.04. Now let us put HL in equation 1, that is here. In place of HF, we need to put that equation. So we got like 4 equal to pressure head plus velocity head plus HL, head loss. So, and we already talk about this pressure head, it's -7. So solving that, length of pipes should be 51.9. So hence we can say that for this system, for not having cavitation problem, the pipe length pump should be installed at 51.9 meter distance apart. Now let us jump into question number 3, which is 4.2.3. This asks us to determine the danger of cavitation, that is a pressure less than 2 by 3 of atmospheric pressure or minus 9.8 lb per inch square. So here it has given for for reservoir A, the uh, water surface is 8 feet below the summit, 8 feet below the summit, and here is also given like frictional head loss, that is equal to 2.5 times the velocity head, and that is evenly distributed throughout its length. And another one is the entrance is square pipe, that means here the pipe is square entrance, and that has key value of 0.5, and when it comes out, that means exit value will be 1. So now from question we got like for point, let us suppose this top be point A and this be point B, and this top of siphon be PS and BS. So for P, for A, velocity and pressure will be 0. So now let us use the energy equation from A to B. So that give us like this form, and our head loss will be equal to, like I mentioned, HF plus H entrance here plus exit. So HF is equal to 2.5 times V square, that means velocity head, and Ke and Kd V square by 2G. So while solving all these, we will have this velocity of 28.9 feet per second. And one of the major thing you should not forget here is unit. The unit of G will be 32.2 feet per second square, because all the units are given in feet, so I converted G meter per second square to 32.2 feet per second square. And I also want to emphasize this. It will be 60 minus 8, because we solved this problem by setting datum at this downstream, so which will be equal to 52 feet. Now since we have B, we can use that in here in the siphon, and from that we can compute pressure. So for finding the pressure at the summit, we can use again energy equation from A to summit of siphon, so which will be equal to this energy equation. So for HA, the head will be 52, whereas this PA will be 0, BA will be 0, HS is equal to 60, and this we need to find this one. We know v square, and this is velocity head. We know the value of v, so we can compute that easily. And for this head loss, here in the question there is clearly mentioned about the distance from siphon entrance to the summit is 1/5 of total siphon length. So I use that 1/5 of head loss, that is head loss is equal to 2.5 times this 28.9 square. This is a velocity. So basically just computing all those numbers, we will have this pressure head of minus 33.92 feet. Now let us convert this pressure head and compare with the cavitation limit. So pressure head will be 32 times 62.3, that is this specific weight, times 1 by 144 inch square, this is feet square, which gives us this 14.67 lb per inch square. Since this 14.67 lb per inch square is less than 9.8 minus 9.8 lb per inch square, cavitation is a real problem. So what suppose you are the engineer, and what could you do to reduce cavitation risks in this siphon? The answer could be like lowering the summit, or increasing the pipe diameter, or smoothing the entrance. So now we are done with the question number 3 as well. Now let us jump into question number 4.2.5, and this is also similar like previous one. It also asks us to find whether there is cavitation problem or not. So here there are two reservoirs, and this is the place where it is elevated. Pipe is elevated for effective downstream flow of water, and question asks us to find whether there is cavitation problem. So one of the before I jump into the solving question, I will I will say that this let us this point be S. The elevated point S is where cavitation can happen most likely, because it is the highest point in the pipe, and second one is head loss have accumulated from entrance. So we need to check whether pressure at S, that means elevated point, drops below vapor pressure or not. So it's like this same like previous siphon problems. So we just need to find velocity for that. So we will apply energy equation from reservoir A to B. Here another crucial thing that you need to remember is here there is gate valve. So we need to take care about this as well. So using the energy equation, we have energy equation, and like height of head of HA and head of HB, they are typically 25 meter, and like I mentioned, we need to consider the head loss from gate valve as well. So we will use from the frictional factor, head entrance, head exit, and head loss from valve. So this give us this formula, and for K entrance it is 0.5, and KD it is exit, so it is 1, and for K valve 1, this gate valve 1, it is a value of 0.15. So here we need to again find F. So what we know? We don't know the F. But we can we know the like surface roughness, which we can compute from E by D. So for smooth concrete, the E is equal to 0.18 mm divided by diameter of pipe, which is 200 mm, and that gives us 0.009. And let us like assume we can assume F friction factor be 0.0195 for the first trial, and this is the hit and trial. You need to be active on this. For now, I directly use the given value 0.095, and when we solve this equation 1, we will have the velocity of 3.98 meter per second. And let us since we have V, then we can verify whether our friction factor value matches with the computed from Modi diagram. So from the Reynolds number, we have diameter times velocity divided by kinetic viscosity. So we have the velocity 3.98, diameter 0.2, and kinetic viscosity at 20 degrees Celsius water is 10 to the power minus 6. That gives us 7.96 times 5, and we have like this 0.009 E by D surface roughness, and by using the Modi chart we also got 0.095. So our assumption about F frictional factor is done. Now let us balance through this point A to this. So length will be 150 meter, and here BS and PS need to be determined. So similarly here we use the energy equation again, and for the top of the siphon, let BS be equal to B, that we already computed. So there is already given delta S, that is 7, and we need to compute this pressure head. We know BS, we need to compute HL. HL will be equal to frictional factor head loss plus entrance. So that gives us head loss of 12.2 meter, and putting this in the above this equation, we have like pressure head of minus 6.01 meter, which is greater than minus 7 meter. So if the pressure head is greater than minus 7 meter, then there is no cavitation problem. Now let us jump into question number 4.2.12, which is bonus question for you. So the question asks us to find the minimum pressure P naught, so pressure at A, that help us to keep the pressure head throughout the pipe positive. That means pressure head should be positive throughout this water system. So, and question asks about bulbs are fully open, bend losses here. Bend losses are neglected, and water temperature is at 20 degrees Celsius. And one of the key insight here is that the most likely location for negative pressure is at highest point and farthest from the pressure source from here. So here 4 and 5 are the highest at the same height, but point 5 is further along, meaning more head loss has accumulated. Therefore, we can check pressure at point 5. So now let us identify critical point. When asked to keep pressure positive everywhere, we need to find the pressure where pressure is lowest. This is typically at the highest elevation point that's farthest from the pressure source. From here, it is 5, and that is most highest point. And height of this 0.5 is 9.5 meter, and has accumulated head more than this 0.4. Now let us set up the equation of energy equation for point A and 0.5. So this here we don't know the pressure P naught, So HA will be 10. This need to be found. Pressure head need to be found. Velocity head will be 0. H5 is equal to 9.5, and pressure head will be we consider as 0 to meet the condition of problem. And so for velocity at 5, let it be b, only b. So this gives us like this equation, and this for HL, it is the HF plus summation of K times B square by 2G, where like here we need to consider the K entrance and this K valve as well, which is 12, and other we don't need to consider. And we can also compute the surface roughness E by D. For commercial steel pipe, E is equal to 0.045 mm, and diameter is 102 mm, which gives us 0.00441. Because we don't know the velocity is still here as well, we can again assume uh, friction factor. Let us suppose now 0.02, not likely turbulent. And here we need to consider the length of pipe as well. Like from A to 0.5, we need to follow the path of this pipe and compute the length, which I have done here. So which give us 32.5. So we have the F, and we have the L as well. We can compute. Still, there will be two unknown, like pressure head and this velocity head. So let us it be equation 1, and now go through this reservoir A and reservoir B, where this velocity will be 0, pressure will be 0, only there will be pressure. We need to find the pressure knot. So we have the equation, energy equation for A and B. So for head loss, we need to consider many things like HF plus summation of K times B square by 2G. So for entrance, we consider value as 0.5, for K check valve, which is 12, and for K globe valve, the value is 10, and for exit, it is 1. So we have another equation, this pressure head equal to minus 2.5 plus 31.34 b square by 2g. So we need to solve equation 1 and equation 2. When we solve that, b will be equal to 3.42. So now let us use like this value of b in equation 1. What we got? B is equal to 1.85 meter per second, and we know since we have now velocity, we can verify our assumed frictional factor with the frictional factor obtained from Moody chart. So let us do by computing Reynolds number. So it's dB by V. V is equal to 1.85, whereas diameter is 0.102 meter, divided by this kinetic viscosity, that gives us 1.89 times 10 to the power 5, and E by D will give us this 0.000441, and from Modi chart we will have frictional factor of 0.185. Now we will use this the chosen value, like f is equal to 0.2, and this from Modi chart f is equal to 0.185. They are similar, so we will use this velocity in the equation 1 to find the pressure head. So that gives us 2.88 meter, but we just need to find pressure. So that gives us like 2.88 times this is 9790, this is specific weight, and that gives us pressure of 28.2 kilopascal. So what happens if the applied pressure is less than 28.2 kPa? The answer will be the pressure at point 0.5 becomes negative and air might be drawn into the system through small leaks or cavitation could occur. So now since we solved all the problems, so here are some summary and the key takeaways. So for solving the problem that are related to uh, head loss, pipe analysis, cavitation, we need to take care about the figure. We need to draw the system and identify all unknown and known and unknown quantities, and we also need to identify the critical points like highest elevation after major losses or pump suction, and we need to apply energy equation between appropriate points, and somewhere we need to assume the frictional factor as well and verify that with the computed one as well. And for cavitation problems, we need to set pressure equal to vapor pressure as the limiting case as well. And some of the common mistakes you need to avoid is like forgetting the minor losses from entrance, exit, or bulbs, and incorrect sign on elevation terms. Be consistent with the datum and not iterating to verify friction factor, and confusion on the gauge and absolute pressure, and forgetting that parallel pipes have equal head loss. So this sums up this week recitation class. Hope you guys will understand some numericals from this lesson. Thank you for your time.